Microphone check, 1, 2. Microphone check, 1, 2. Microphone check, 1, 2. Hello, geometry students. Mr. Zacek back with you. In Unit 7, Lesson 2. Here we go. All right, shaking it up a little bit. We are talking today about similar polygons, okay? So when we hear the word similar, how we define that is that they have the same shape, but not necessarily the same size, okay? Not necessarily the same size. So the symbol for that is this little, what we see right here. If we think of it as kind of the top part of a congruent symbol as the same shape. So that's kind of a more vernacular definition. If we're going to get a little more specific, and this is what we want to get more specific, is two polygons are similar if, number one, corresponding angles are congruent, and number two, the lengths of corresponding sides are proportional. So we've got congruent corresponding angles and proportional corresponding sides. So when we think about similarity, like examples of similarity are maps use this a lot. When we have like scale factors, use similarity. Any kind of modeling, so like a model car or some kind of architectural, drawing, all that stuff. So drawings, for architecture, engineering, all this stuff uses the idea of similar. So if we look at this example, we've got a quadrilateral. So ABCD is similar. Again, this little thing means similar here. So it's similar to GHIJ. And you can see here what we've got the angles and then we've got the sides. Now, what I do when I'm setting up these, the proportions or the fractions and the ratios, I put one figure on the top. So you'll notice, like in this particular diagram here, that, hang on, I'm going to pause this so I can recalibrate. Okay, back with you. So you'll notice like this figure here, in this proportion, all of those are on the top. And then in this figure here, those are the ones that are on the bottom. So the corresponding sides are in one figure. So there's other ways of doing it. I just find for me that that's the best way of doing it. So when we have the scale factor is the ratio of corresponding linear measurements of two similar figures. So the ratio of two corresponding sides, in this example, we've got triangle ABC similar over here. Board's being a little funky today. So similar, triangle ABC is similar to XYZ. So notice sides BC corresponds to side XY. So what we're looking at here again is looking at the order of these letters. So BC over XY is 20 to 8 or 5 to 2. Now that shouldn't be XY, that's incorrect. I was looking at that and I was like, wait a minute, that doesn't make sense. That's incorrect, so let's fix that. So it should be BC and over YZ. Those are the ones that correspond. And you can look at like their positioning in the statement where they are. So 20 over 8, we always want to reduce that. And so the scale factor is 5 divided by 2 or 5 to 2. You can write it either one of these ways like we talked about in our last lesson, okay? So scale drawings are an example of this. All the lengths are proportional to their corresponding actual lengths. The scale is the ratio that compares each length in the scale drawing to the actual length. So 1 inch could equal 100 miles. So this is, again, what you'll see if you're looking at a map, or if we're doing a drawing of a building, any kind of floor plans, you're going to have some kind of scale. So let's look at this. All right, so number one, so beginning here, first thing let's recognize is this is what's called a similarity statement. So we're just saying here that those two triangles are similar, and what pair of angles are congruent? Well, we can actually look at this in the order of the letters. So angle M is going to be congruent to angle S. Those are the first letters. Angle N is going to be congruent to angle R. And angle P is going to be congruent to angle T. So if we're going to mark that over here on the diagram, it would be M and S are congruent, and then N and R, and then P, 1, 2, 3, and T, 1, 2, 3. So if we're going to look now at the corresponding sides, sometimes that's a little bit trickier. So we got 3 sides, so we're going to write 3 fractions. So I'm just going to start with triangle MNP, and maybe I'll do MN first, and then NP, and then MP. And now I'm going to figure out which ones correspond. Well, look at M and N. So that's our 1 mark and 2 marks. And this other one, our 1 mark and 2 marks are SR. So it corresponds to SR. NP, N has 2 marks, P has 3 marks. So that would be RT over here. And then MP, 1 and 3 markings with M and P. So S and T are the ones that correspond to that. And again, there's a bunch of ways we could write that are equivalent, but that's, how I do. Pick one triangle, put those in the numerator. Pick the other triangle, the sides that correspond, put those in the denominator. Okay, so are the polygons similar? If so, if they are, write a similarity statement and find the scale factor. So we're going to look at, we want to assess those 2 things. So number 1 is, are the corresponding angles congruent? That's our first question. In this particular triangle, or quadrilateral, that's true. Okay. So we move on to the second consideration, and that is, are the corresponding sides proportional? That's going to take a little more work to answer this question. So we've got, in a quadrilateral, we've got 4 sides. So I'm going to start with side, I'm just going to work my way around, and we've got 6, 12, 24, and 24. Okay. So as I look over here at MJKL, do you see how the 6 goes from the 1 to the 2 marking? So over here that would be WT, so that would correspond with 6. Well, in JK is 12, JK is 12, but TU is 6. All right, and then I'm just kind of working my way around. Here the next side, 24, is 16, okay, and then 14 is our last side. So again, these are all question marks. Are these equal to each other? So we go ahead and we reduce that, and it does 1 equal 2? No, it doesn't equal 2. Doesn't equal, this would be 3 halves, which doesn't equal 12 sevenths, okay? So therefore, they are not similar, because it doesn't meet both of those criteria. It's not just enough to have the angles in the quadrilateral, we need the angles in the side. All right, now for B, so let's try this here. So again, so congruent corresponding angles. So the question is that true? And that is true. Okay, and so then let's look at proportional sides? We want to ask that question. Are the sides in proportion to each other? So this one, we got 3, okay? And these are all question marks. We don't know if they're equal. I'll just start and go 8, 12, and 16. I pick one triangle and I put them in the top. So you see how 8 is between the 1 and the 2 markings, so C and A. Over here, that would correspond with 10. Okay, so then the 12, that's between 2 markings and 3 markings, so that would correspond with 15, and then that would leave 20 as our last one. So now we want to reduce 8 and 10, 2 goes into both of those, so that would be 4/5. Okay, 12 and 15, 3 goes into both of those, 4/5, and 16 and 20, 4 goes into both of those, 4/5. So yes, we could say that triangle ABC is similar to triangle, if we started with A, we need to start with DEF. Okay, so that's our similarity statement. Okay, now as we look here at number 3, we are told that they are similar. So this is a similarity statement. ABCD similar to EFGD. What is the value of X? So we're looking for, in this scenario, what we're looking for is we're looking for corresponding parts here that we know. So if we take this big trapezoid, or which looks like a trapezoid, I'm going to look at this side AD, which is 9, and AD corresponds to ED. See how the 9 and the 6 correspond? So you're looking for one where you know both of the numbers. That's kind of like our scale factor, if we think of that. Now X is over here, it's on the smaller one, so X is FG. What side does that correspond to? That corresponds over here to 7.5. So now what we can do at this point is we can use our cross product property, and we'll get 9x equals 6 times 7.5, okay? And 6 times 7.5 is 45. So 9x equals 45. Well, we divide 45 by 9, we get 5. So x would equal 5 in this scenario. Okay, so the okay, so now number 4, your class is making a rectangular poster for a rally. The poster's design is 6 inches high by 10 inches wide. The space allowed for the poster is 4 feet high by 8 feet wide. What are the dimensions for the largest poster that will fit in the space? Okay, now these are tricky questions, and this is a good question if you were trying to maximize something and keep the ratio. You want to think about this like if you have a picture, this is the difference between grabbing it in the corner and when you enlarge it, you keep things in the same proportion. So that's what our goal here is to do in this case. So what I do when I think about these questions is, okay, I've got a 4 foot by 8 foot wide. Now I'm going to convert that to inches because my design is in inches. So 4 times 12 is going to be 48 inches. This is not drawn to scale. By 8 feet wide. So let me redraw this just to make it look a little more realistic. Okay. So 48 by 8. So 8 times 12 is 96 inches. All right. And in the top of this, I've got this 6-inch by 10-inch kind of poster, and I want to expand it. So my question is, the question I'm trying to answer is, in order for this to go, which of these dimensions will fill out this space first? Okay? And what I realize is that this, if I drag this down, 6 times 8 is 48. So if we take, excuse me, hang on one sec. So 6 times 8 is our 48. So what will happen is this side of it will hit the bottom part first. And because the other one, 10 inches, well, 10 times 9 would get us to 90 inches, but we still wouldn't have that whole thing filled out. So, but I need to figure out how far that will go. So 6 over 10 is going to start off with 48 inches, so the 6 will fill the 48, and I want to know when that happens, how far will this other side go? And some of you probably already know the answer. 6x equals 480, and when we divide by 6, 480 divided by 6 is going to be 80. And some of you might have known that. So 80 inches. So the largest dimension for the poster would be 48 inches by 80 inches. Okay, so again, if you're not sure, just, you can just kind of check mark that off, not drawn to scale. Figure out which one it's going to fill first. So this time it was the height that would fill first, and then we got to figure out, okay, if the height is 48 inches, what does that mean for the width? Okay. All right, we got one more question here. The diagram shows a scale drawing of the Golden Gate Bridge in San Francisco. The distance between the two towers is the main span. What is the actual length of the main span of the bridge? So in this case, it's just a proportion. We know that 1 centimeter equals 200 meters, and we know in our diagram that 6.4 centimeters will equal x. So that's going to be the actual one. So we cross multiply and we get x equals 200 times 6.4. We're not really concerned about units here in this case. So it's going to be 200 times 6.4, which comes out to be 1,280 meters. So that's a pretty long stretch. I have a friend of mine whose son for a while was a painter on the Golden Gate Bridge, and there's a lot of corrosion that happens from the water, and actually what they do is they start painting the bridge from one side, and when they get done painting they go back to the other side and they start painting again because the paint erodes that fast that's how often they have to do it. Of course it takes a long time to paint and you have a nice view as you're doing it, but little story. Okay, so ratios, proportions, similarity, looking at those things. Again, the two key things here: corresponding angles are congruent, corresponding sides are proportional, and looking at similarity statements and the notation that we have for those and scale factors. So good luck with your assignment, and I will see you back here soon.